In the last video, we learned about the stereoisomers and the chirality definition. So we know that the stereoisomers, they are molecules that have the same molecular formula and same bond connectivity, but they have different spatial arrangement. Stereoisomers are non-superimposable, and generally they have a relationship with one another. That relationship can be divided into two categories. If the molecules, the two stereoisomers that we are looking at, they are mirror image of one another, they are enantiomers. So if the two stereoisomers are not mirror image of one another, we call them diastereomers. So examples here, we have a cis and trans isomers. We want to know whether they are enantiomers or diastereomers. So if you look at these molecules, we have cis isomer here and a trans isomer here. Now if you imagine there is a mirror here, they are not mirror image of one another. So cis and trans isomers, they are always diastereomers. Enantiomers, so once again, they have the same molecular formula and connectivity, but they have different spatial arrangements. So they are stereoisomers and they are non-superimposable. Enantiomers are mirror image of one another. So how do we draw an enantiomer for a single molecule? If you look at the molecule below, there is a chiral center in this molecule right here. There are two ways that you can draw its enantiomer. The first way is basically imagine there is a mirror here and draw its mirror image in front of it. So I'm gonna do that. All right. So this is the mirror image of this molecule. Of course, therefore it's enantiomer. They are enantiomers. Now the second way to draw the enantiomer is to redraw the molecule. Redraw the molecule with the same bond connectivity. All right, chlorine is right here. Now, you need to flip the stereochemistry to get the enantiomer. So if it is in wedge, I need to draw this bond in dash. So redraw the molecule and flip the stereochemistry. Now these two molecules, okay, they are the same molecule. So if you make the model of this one and flip your model, you get this molecule. So both of them are the same molecules. You can draw them in either way, right? They are the same. I personally prefer the second way while drawing the enantiomers. It's easier to follow, I believe. So if you redraw the same bond connectivity as you see and just flip the stereochemistry, it's easier sometimes rather than drawing the mirror image. And another important point here is remember that you can only draw one enantiomer for a single molecule. So basically, when you look at the mirror, there is only one of you in the mirror, right? There is only one mirror image of you there. So you cannot draw multiple enantiomers for a single molecule. There is only one mirror image for that molecule. Diastereomers, again, they have the same molecular formula and bond connectivity. They have different spatial arrangements, so they are stereoisomers and they are non-superimposable. So till now, it's similar to enantiomers. Now the difference here is diastereomers are not mirror image of one another. So to be able to draw the diastereomers for a single molecule, you need to have at least two chiral centers in the molecule. You can have more than two, but at least two is required. So how can we draw diastereomers for a single molecule? There are multiple ways of doing that. I found this way easier, so I'm going to teach you this, which is pretty easy. So the way to do it is first redraw the molecule with the same connectivity. So I'm going to do that. I have chlorine connected here and OH connected here. Now, to make this molecule a diastereomer for the first molecule, you need to flip at least one stereochemistry and keep at least one stereochemistry the same. So, to do so, this one is in veg, chlorine is in veg, so I want to keep this one the same, and I'm going to flip the OH. So this one stays the same, and I'm gonna flip the OH. So OH is in veg right now. Now I can do it actually in the other way. So basically what I can do is to have the same bond connectivity. Now I want to keep the OH the same, the stereochemistry of the OH the same, and flip the chlorine. So I need to draw both of them in dash. Okay, so both of these molecules are diastereomers for this molecule. So we can draw more than one diastereomer for the single molecule. So both of these, they are diastereomers for this molecule. Now, if I want to draw its enantiomer, again as a practice, I'm gonna draw the same bond connectivity. Now I need to flip everything. So this is chlorine and OH, and to flip that, chlorine should be in dash and OH must be in veg. So this is its enantiomer. Now there is a formula which is 2 to the power of n, and n is the number of chirality centers. So using this formula, you can decide how many stereoisomers you can draw for a specific molecule. So for example, here we have 2 stereocenters. Therefore, this should be 2 to the power of 2 gives me 4. So I can draw 4 stereoisomers for this single molecule. One of these 4 stereoisomers definitely is its enantiomer, and the rest are its diastereomers. So 4 stereoisomers for this molecule. One of them is its enantiomer, and the other 2 are its diastereomers. Now, enantiomers are not identical, so they must have different names. We know that enantiomers are mirror image of one another, but they are not superimposable, so they are not identical. Now, how do we differentiate between them? So if you look at these 2 molecules, they have the same connectivity, so we can write the same name for them, 2-chlorobutane. Now, to distinguish between these 2 molecules, there is a system that we need to follow called Cahn-Ingold Prelog. This is just the name of 3 scientists, and these scientists, they designate each chiral center as R. R is coming from rectus, meaning right in Latin, or S coming from sinister, meaning left, to the molecule. So here we have 2-chlorobutane, both of them, but one of them is R isomer, the other one is S isomer. all right? So both of these are enantiomers. Now, a very important point here. Enantiomers have different R and S designation, okay? So if one of them is R, the other one should be S. Now, how do we assign R and S to the molecule? Designating R and S using this system. So there are a few rules that we need to follow. The first one is that we use the atomic number to prioritize the groups connected to the chiral center. So we know that the atomic number from left to right in the periodic table and top to the bottom increases. So you can use this trend to prioritize the atoms connected to the chiral center. Now, if you look at this molecule, the example below, this is a chiral center. We have chlorine attached to it, oxygen, carbon, and hydrogen. Now, if you look at the periodic table, atomic number for chlorine is 17, oxygen is 8, carbon is 6, and hydrogen is 1. So, the trend or the order would be 1, 2, 3, 4. Now, after doing that, you need to arrange the molecule in a space so the lowest priority group faces away from you. If you look at here, the lowest priority here is hydrogen. It is in wedge, meaning that it is pointing toward us. So what we need to do is to rotate the whole molecule. So basically, replace 2, 3, and 1, 4. Now the lowest priority is pointing away from us. After doing this, we need to start counting the priorities 1, 2, 3, and we always leave out 4. So if you look at here, it's 1, 2, 3, 1, 2, 3. Look at the movement of my cursor. It is counterclockwise. So when the movement is counterclockwise, this chiral center is S. And vice versa, if the movement is clockwise, that chiral center is R. Now, sometimes the molecules that you are dealing with are very complicated, so it's not always easy to rotate the whole molecule. There is a trick here. If you look here, look at this molecule, what you can do is to start counting. After giving the priorities, start counting. So it's 1, 2, 3. Look at the movement of my cursor. It is 1, 2, 3, 1, 2, 3. It is clockwise. Now, because the lowest priority is pointing toward us, you need to flip that. So the movement is clockwise, which means R. Now I need to flip it so the chirality center is S. Okay? Okay, so a practice problem. Let's assign R and S for the chiral center in this molecule. So there is a chiral center in this molecule right here, because let me draw the hydrogen connected to this carbon. So to this carbon, we have NH2 attached, hydrogen, oxygen, and carbon. So 4 different groups attached. It's a chiral center. Now, to determine the configuration, we need to assign priorities according to the atomic number. If you look at the periodic table, oxygen gets number 1, nitrogen is 2, carbon is 3, and hydrogen is number 4. Then we need to start counting 1, 2, 3. So this is 1, 2, 3. I'm rotating counterclockwise, so the configuration should be S. However, the lowest priority is pointing towards me, therefore I need to flip the configuration, so it should be R. Another important point here is when you have hydrogen attached to the chiral center, always remember the hydrogen would get the lowest priority because we don't have any other atoms that has lower atomic number than hydrogen, which has the atomic number of 1. So whenever you have hydrogen attached to the chiral center, it is always number 4. And you need to assign the priorities to other groups connected to the chiral center. Sometimes while numbering the groups, you'll see a tie happen. So for example, here we have a molecule. There is a chiral center in the molecule. So this carbon is connected to OH, hydrogen, and 2 carbons. So obviously, oxygen is number 1 and hydrogen is number 4. These are lowest priority. Now, between 2 carbons, so which one is number 2, which is number 3? If you look at this carbon, it is attached to 1 carbon and 2 hydrogens. And if you look at this carbon, it is also attached to 1 carbon and 2 hydrogens. So we have a tie here. In this situation, what we need to do, we need to move to the next layer, meaning that from here, I need to move to this carbon, and from here, I need to move to the next carbon. All right, so now let's take a look at the second layer. So if you look at this carbon, it is connected to 2 carbons and 1 hydrogen, and this one is connected to 1 carbon and 2 hydrogens. All right, so if you compare these two, we have 2 carbons, 1 hydrogen here, and 1 carbon, 2 hydrogens here. So comparing the atomic numbers, this part wins. So it is my second priority, and this part is my third priority. Now, a very important point here. Pay attention when I want to basically count the groups connected to that specific center. I always move forward to the next atoms connected. I never come backward to count the previous atoms. So be very careful while doing that. Now, this one is my second priority. This is my third. Let's assign R and S for this center. So I need to count 1, 2, 3. 1, 2, 3, 1, 2, 3. The movement is counterclockwise, so I can assign S. Now let's look at the lowest priority. It's coming towards us, so I need to reverse it or flip it. Therefore, this is R. A very important point here is when you want to count double bond, you need to count it as 2 single bonds. So what does that mean? Here is the chiral center, which is connected to the carbon that is double bonded to oxygen. So if you want to count the connection here, I need to count the oxygen twice. So this carbon is connected to oxygen 2 times and also connected to hydrogen. Some practice here. So let's assign configuration for these molecules. The first one, we have a chiral center here, which is this carbon. It is connected to OH, methyl group. It is connected to this group. Now, this group, so we have double bond here. This double bond is a point of difference between these 2 parts of the molecule. So we have 4 different groups connected to the carbon atom. So this is our chirality center. Now to assign R and S, we have oxygen. So obviously oxygen is number 1. Then we have carbon, carbon, carbon. Now we need to decide which one is our basically the next priority and which one is the lowest priority. So this carbon is connected to 3 hydrogens. All right, so we have 3 hydrogens connected here. Okay, this carbon is connected to 1 carbon and 2 hydrogens. 1 carbon and 2 hydrogens. This carbon is connected to the hydrogen, and it is like connected to 2 carbons because there is a double bond here. So we have carbon, carbon. Now by looking at this this is our second priority, this is our third priority, and this is our fourth priority. Now to assign RNS, we need to count 1, 2, 3, 1, 2, 3, so it is counterclockwise, and our lowest priority is in the back, so pointing backwards, therefore this is S configuration. So another way to give the priority, majority of the time you can use that. You can assign the priority by looking at the number of hydrogens, and the one with most number of hydrogens gets the lowest priority. So if you look at here, we have CH3, it has 3 hydrogens. This one has 2 hydrogens, this one has 1 hydrogen. So the one that has more number of hydrogens gets the lowest priority. So this is 4, 3, and 2. You can also use that to assign the priorities. Now the next molecule, we have a chiral center here. Again, it is right here. So we need to assign priority. This molecule is a little challenging, but let's do it together. So this carbon is connected to the carbon, completely different group here. Again, completely different group here, and completely different groups. So, and the last one, like the fourth group, is hydrogen right here. So hydrogen is our number 4, we know that. Now we need to assign 1, 2, 3. So this carbon is connected to 1 carbon, 2, and 3 carbons. So it is 1, 2, 3 carbons. If you look at this carbon, it is connected to the hydrogen and 2 carbons because we have double bond. So we count it twice. So, and this one, it is connected to 1, 2, 3 carbons. Right? So again, carbon, carbon, carbon. By looking at this pattern, obviously this carbon is our third priority because it has 2 carbons and 1 hydrogen. However, these two have 3 carbons. Therefore, this is going to be our third priority. Now, between these two, we have a tie, so we need to move forward to the next carbon. So we need to look at this carbon. This carbon is connected to 1, 2 carbons and 1 hydrogen. So this is carbon, carbon, hydrogen. And if you look at this carbon, it is connected to 1 carbon. Now, I told you you don't need to count backward when you have double and triple bond. However, you need to count it only for 1 bond. The other 2, you need to count them. So this carbon is connected to 1 carbon, 2, and 3 carbons. Now, between these two, this one has 3 carbons, this has 2 carbons and 1 hydrogen. Therefore, my first priority would be this chain, and second is this one. Now we need to count. So it's 1, 2, 3, 1, 2, 3. I am rotating clockwise, and my lowest priority is backward. So the configuration here is R. Now, how do we name the stereoisomers? So we learned how to name molecules previously. We are following the same sets of rules here. But to differentiate between the isomers, we need to assign R and S configuration to the chiral centers. So here in these 2 examples, we have 2 molecules and each has a chiral center. Both of them are enantiomers. So this is our chirality center. Now to assign the priorities, most of the time, or I can say all the time, when you have a chain of hydrocarbon connected to the chiral center, only carbon and hydrogen connected to that, the chain that has more number of carbon, it always gets the higher priority. So if you look at here, bromine is number 1, then I have CH3 connected to this center and isopropyl connected to this one, so I have more number of carbons here. Therefore this is 2 and 3, and I know that my last or my lowest priority is hydrogen right here. Now we need to count 1 2 3, so 1 2 3 1 2 3. I'm moving clockwise. Now my lowest priority is pointing towards me, therefore I need to reverse it or flip that. So this is S isomer. And to name the molecule, what you need to do is to put the S configuration before the name of the molecule. Now for the other one, as I said, they are enantiomers, so I don't need to do any assigning. I automatically know that this is gonna be R isomer because they are enantiomers. This slide is very nice to look at to learn the difference between enantiomers and diastereomers. So any two molecules that are in the same green box, they are enantiomers. So these two are enantiomers. And they have 6 diastereomers. So this one is the enantiomer for this one, and it has 6 diastereomers. So as long as there is at least 1 point of difference in the configuration, they are going to be diastereomers. And we know that diastereomers are not mirror images. However, enantiomers are mirror image. So meaning that the configuration are completely switched. So if you look at this molecule, all of these groups are in wedge. To draw its enantiomer, you need to draw all of them in dash. All right. You can even look at the configuration. So this is 1R, 2R, 3S. Now in its enantiomer, all of them must be flipped. So it is 1S, 2S, 3R now. Now if you look at this molecule, this is its diastereomer. So again, these two groups are in wedge. We have them in wedge, and the point of difference is right here. This is wedge, that one is dash. You can even compare the configuration. So you have 1R here, 3S, 3S here. This one is 2R, this one is 2S. So we need at least 1 point of difference to have the diastereomer. There is an easy calculation that I talked about before. You can use that calculation to know how many stereoisomers you can draw for a single compound depending on the number of chirality centers. So the maximum number of stereoisomers can be calculated using 2 to the power of n formula, and n is the number of chirality centers. So let's look at the structure of cholesterol and see how many stereoisomers we can draw for that. So the first step is to identify the chirality centers. Cholesterol has 8 chirality centers. So they are right here. Now if you do the calculation, 2 to the power of 8, it gives you 256 stereoisomers for this molecule. That's a huge number. So among these 256 stereoisomers, one of them is the enantiomer for the cholesterol, and the rest are its diastereomers. So you can easily use these calculations knowing the number of chirality center and figure it out that how many stereoisomers you can draw for a single molecule. So enantiomers have same physical properties. They have the same formula and bond connectivity. So they have the same physical properties because physical properties is determined by intermolecular interactions. And these interactions are the same for enantiomers. So special arrangements can't influence these interactions or change them. Therefore, for example, here in these two examples, in one of them bromine is going backward, the other one is coming towards us. But this difference cannot influence the physical properties. However, enantiomers show different behavior while exposing to the plane polarized light. Now, what is plane polarized and unpolarized light? So, unpolarized light is the light that is going in every direction. So, the lamp that is on in your room has unpolarized light. However, plane polarized light is whenever you shine light in the sample in only one direction. So enantiomers will rotate a plane polarized light in two opposite directions. So if you have plane polarized light coming to your sample, if you put your sample of enantiomer in the polarimeter and shine it with plane polarized light, it will either rotate the light in negative or positive direction. So different enantiomers rotate the plane polarized light in the same extent but in opposite direction. So if you look at same example, we have S isomer here and this one is R isomer. Both of them rotate the light to the same extent with the same number but in opposite direction. One of them is positive, the other one is negative. If the enantiomer shows negative rotation, it is called levorotatory, and if it shows positive rotation, it is called dextrorotatory. So you don't need to use negative or positive. Sometimes you may see that small l or d while naming biological structures. You don't need to use them while naming organic molecules. What you need to know is that enantiomers can rotate the plane polarized light in opposite direction, and that's the only physical difference between them. More practice problems. Let's look at these molecules and determine their relationships. Are they constitutional isomers, enantiomers, diastereomers, or identical? To answer these types of questions, you first need to check whether the molecules have the same molecular formula. If they do, you need to check the connectivity. Do they have the same connectivity? If they don't, they are constitutional isomers. And if they do, you need to think about stereoisomers. Then you need to find the chiral center, whether you have a chiral center in the molecule or not, and think about enantiomeric or diastereomeric relationship. So if they are mirror image of one another, they are enantiomers, and if they are not, they are diastereomers. Now let's take a look at the first sets of molecules. These two molecules, they both have the same molecular formula, but as you can see, we have two different connectivities. This one has 1,2-methyl groups. This one has 1,3-methyl groups. So they are constitutional isomers. Now, if you look at these two molecules, they have the same molecular formula. They have the same bond connectivity, so they are not constitutional isomers. Now you need to think about stereoisomers. Do we have chiral center in these two molecules? Yes, we do. So we have two chiral centers here. Now we need to ask ourselves, are they mirror image of one another? Yes, they are. So if you imagine there is a mirror between these two molecules, they are mirror image of one another. Therefore, They are enantiomers. Now, if you look at these two molecules, again, same molecular formula, same bond connectivity, so they are not constitutional isomers. We need to think about stereoisomers. And in this one, both methyl are pointing to the same direction. However, in this one of them is pointing this way, the other one is pointing that way. So this is the cis isomer, this one is the trans isomer. And we already talked about that. Cis and trans, they are diastereomers. Now let's look at this molecule, this one right here. Again, we have same molecular formula, same bond connectivity, so they are not constitutional isomers. Now we need to think about the stereoisomers. Do we have chiral center? Yes, we do. So we have one here and one here. Now, are they mirror image of one another? They are not mirror image of one another, so they are diastereomers. Now let's look at the last molecule. So the last molecule can be a little bit tricky. Again, we have same molecular formula, same bond connectivity, so they are not constitutional isomers. Then we need to think about stereoisomers. Do we have chiral centers? Yes, we do. So we have chiral centers right here. Now, something you need to consider, if you make the model of this molecule is rotated in space around this bond and converted to this molecule. So basically both of them are the same. This is just rotated around the carbon-carbon single bond. Therefore, they are identical. So they are superimposable to one another. You can put them on top of each other. Therefore, they are identical. This is the flowchart that I designed for you. I believe it's going to be very helpful while assigning the relationships between two different molecules. So given two molecules with the same molecular formula, you need to ask yourself, do they have the same connectivity? If they don't, they are constitutional isomers. If they do, you need to start thinking about stereoisomers. Now, you need to ask yourself, are they superimposable? If they are identical. They are not stereoisomers. You have a single molecule. Now, if they are not superimposable, you need to ask yourself, are they mirror image of one another? If they are enantiomers. And if they are not, you have a pair of diastereomers.